Okay, so we have a 7-point orbit problem here. It's pretty straightforward. You take a quick look at it, you're going to see something that looks like a circle. Kind of read down, just glance over it a little bit, and I see the word circular orbit. So that's a good thing. See, then I'm looking at a figure below. I see forces, not components. That's a free body diagram. You need to make sure I use a pencil on that. Also, that's probably worth some points. Now I see, so my guess is like 1 to 2 points on that for a 7-point question. So let's say 2. And I see derive. This is going to be the big part. But remember, you only want to go for a couple of points and not get caught in an algebra trap. So we wanted an equation. Has to do with all those m's and r's and a constant. What is it for? It's for time periods. So this looks like circular motion. I know time period's 1 rotation, and I know it's a circle. So keep that in mind. 2 check boxes, yeah. Those definitely are, one's 2, one's 3, because these are usually 1 each. Not always, but usually. Okay, so yeah. Do I have to draw another picture? Nope, just a check box. So just a quick run through on it. So now it's time to start reading the question. Figure's not drawn to scale. That's just telling you that they can cheat you on the picture. So a spacecraft of mass m is in a clockwise circular orbit. Okay, so circular and orbit. Orbit means it's a constant speed. Clockwise means that it's going negative, but I don't think that's going to be super important. The spaceship is M, and it's going around the Earth. It's got R, and it's shown in the figure above. And the mass here, made a mark there, that's the mass of the Earth is ME. So we got big M, little m. All right, so this one. In the figure below, draw and label all the forces, not components, that act on the spacecraft. Each force must be represented by a distinct arrow starting on and pointing away from the spacecraft. That tells me that the spacecraft is supposed to be my center of mass dot, because that sounds just like what you're supposed to do on a free body diagram. So I know this is in circular orbit. The trick here is they say forces. If this is in circular orbit, it's probably just one force acting on it. And since I know it's not tension, friction, or normal force, because there's nothing, it can't be a contact force, I know that this is going to have to be big force of gravity. So G, M, I'll go and put the E, little m, that's the mass of the spacecraft, and that is all R, like the drawing said, away from the planet. And since I can see the curve, circle, that's R squared, the inverse square law, the butter toast. So you don't have to write this here, but to me that just popped into my mind. So I'm going to draw a line straight in. I'm going to put an arrow on it, make sure it's touching the spacecraft, and I'm going to label it F sub G. So I bet that's a couple of points. And it turns out I was right. This is what you're supposed to have. Looks a lot like what I drew. There's prettier. So you get a point just for having the arrow without a label. And then you get another point for labeling it. And if you messed up and drew applied force or something crazy, you still get a point. That's not the case on all of them. All right, so for the second part, derive, that means at least 2 equations. It probably needs to come from a law. And you know what? Before I even read this, I can already tell you what it is. We got a free body diagram. Hopefully you know that is Newton's second law. I would just write that. Net force equals your mom. Just kidding, your ma. The sum of all forces equals mass times acceleration. Then it's going to need to equal whatever is in this diagram. And that can be any free body diagram. So I know that that is the gravitational force. But let me keep reading. Derive an equation for the orbital time period t. I'll probably use a different color pen here, like my blue pen. Okay, that's kind of weird. That's how long it takes to go around the spacecraft in terms of all the masses and the radius and physical constants. It's appropriate. Those are on the back, on the pink side of the equation sheet. Okay, they're warning you not to draw anything else. They're very picky. Do not add anything. Well, let's go ahead and break this down. I know this would be centripetal acceleration because it's in uniform circular motion. The force is directed towards the center. And I also know I've already written that equation for F sub G. So let me just go ahead and set these 2 things equal to each other. Okay, so I went ahead and set the mass times centripetal acceleration and the at a distance gravitational force equal to each other. And I did notice that some things cancel out. Take care of these little limbs. And if you see these cancel out, you can just cancel them out. You don't have to do this. I'm just doing it. Okay, and looks like we got some R's that cancel out maybe. So that's going to give you v tan squared. You don't have to write the tan there. It's a habit. Gravitational constant, mass of the Earth over R. And the only problem here, I've got a constant, I've got mass of the Earth and R, is I still don't have time period. But I know I'm in a circular orbit. So right down here, v tan. When you're in a circular orbit, it is just how far you go, which is the circumference, 2 pi r, over how long it takes. And that's one cycle. That's how long it takes to make the circumference, so that's time period. This looks like it'll work. Now, I notice I have this squared up here. This is just a time-saving trick, but what it works for me, whatever works for you. I would just go ahead and square this down here. So I know I'm going to have 2 squared, pi squared, r squared, and t squared. So I'm going to put that in. 4 pi squared r squared over t squared equals, and really at this point I've probably gotten the majority of the points, but I want to know the answer. G, mass of Earth, over R. And it looks like some stuff could cancel. Okay, so I'm going to use a purpley colored red pen thing here. Remember, you can only use blue, black, or pencil on the test. So I'm going to go ahead and solve this for t squared. Just going to put it on top real quick. Okay, so at this point, I would want to go ahead and just solve for t squared. Okay, so at this point, I basically have t squared equals all of this over here. Okay, sorry about that. There's a little bit of gap there. So basically, at this point, I have t squared equals, let me put the number first, 4, and then anything that's not squared, pi squared, and then that looks like r squared times r, so it's r cubed, over gravitational constant, mass of the Earth. This looks weird. Oh, it's squared. I'd probably leave it squared, but you can always square root. And then you can square root each one, but I'm kind of running out of room, so I'm going to square root the whole thing. Just be careful that dips all the way in. And I'm kind of lazy. I just scratch these out and just circle that as the answer. That looks weird. This last step, if you're short on time, I wouldn't have done. Let's see how it did on that. Okay, yep, that's exactly what I put. We got, it says you can imply, that means you can just set everything equal. I would think this would be enough. But it's always safe to write Newton's second law somehow. So that's a point for explicitly or implicitly. So that means you could have just plugged it right on in for the 2 pi r for a correct answer, which we had. And oh, look, my laziness of not wanting to square it would have been just fine. So there you have it. Okay, on to the check boxes. From what I saw, people did a pretty good job on this. But usually when you have check boxes, you can reference one of your equations, so it's probably a good thing. So this is a second spacecraft of 2m is placed in a circular orbit with at the same time as radius r. The orbital period of this spacecraft is greater than, less than, or equal to. So basically what's happening is they're just changing the mass. So what I would do, let's go back over here. They're changing the mass of the spacecraft type object. If you notice, time period, you can't use highlighters on the test. I'm just doing this to make it's kind of messy. So if you notice, time period has nothing to do with the mass of the spacecraft. So Whoops. Let's go back and look at that. So since mass has nothing to do with this, I would check equal to, and I would put time period time period is not affected by mass. C, work on BI. Okay, that works for that one. Okay, so now they do something else. Oh, it's kind of broken. The first spacecraft is moved to a new circular orbit as a radius greater than r. I think that's supposed to be r, as shown in the figure below. So it's a new orbit, it's further out. Is the speed of the spacecraft in the new orbit greater than, less than, or equal to the original speed? Okay, here's what you can do. I was pretty sure that I had VTAN somewhere in here. And you actually have that like in your original equation here. So I had VTAN squared, and it is related to the radius. So I'm going to actually just take this equation and move it over there. Okay, so for my other one, I had VTAN squared equals G ME over R. Okay, I'll maybe put from B part I. Therefore, VTAN squared is inversely proportional to 1 over R. Even though that's squared, you could do the square root thing or whatever. It's still, if radius goes up, VTAN is getting smaller one way or the other. So I would put that it is less than. Here, I'm going to put my because. Yep. And this is that's fine for your justification. Let's take a look at these two real quick. It says, okay, this one's worth 1 point. You had to put equal to. If you had some kind of good explanation that was consistent with the other one, I guess it might be graded. Basically, they want to know that the period of the spacecraft does not depend on the mass. Oh, what this means is if you had messed up your equation in the first part and you worked on the assumption that it was correct, then you wouldn't lose a point. Okay, and then for the next one, yep, less than was right. If the wrong selection was made, you're out of luck, and they want an explanation. So, derivation in step BI shows the speed decreases with increasing R. Good to know.